These sets of lessons will introduce you to a variety of exercises about limits. We will begin by introducing basic limits. I will try to annotate this document with a yellow color so you understand when am I doing any change to that written document. So first I'm given a function f of x, and f of x is equal to x minus 1 over 2x plus 5. In order to find the limit on that function as x approaches 0, first you try a simple substitution approach. You plug in, since x is approaching 0, plug in x equals 0 in x in the numerator and x in the denominator. This will yield negative 1 over 5. And this is a simple substitution approach of x equals 0 in f of x. Technically, you're asking the y value, so I reduce the thickness of the color. We're asked for the y value at a certain x value. In this case, x equals 0. So that would be technically the limit in this case. In the second case, we're asked to find the limit of the function f of x as x approaches negative 5 over 2. Now, negative 5 over 2 is a value that will make the denominator 0. And in this case, the whole function will be undefined since the denominator is 0. We could try first by doing a substitution, and when you substitute negative 5 over 2 in this x, negative 5 over 2 in this x, you'll quickly see that the denominator becomes 0. So in this case, that is a case of a vertical asymptote. So where the denominator is equal to 0, the x value where the denominator is equal to 0 represents a vertical asymptote on the function. And in this case, the limit does not exist as the function behaves either towards positive infinity or towards negative infinity. So when you're sketching this, if you have an xy axis, and at x equals negative 5 over 2, the function will either behave as such, or maybe from the other side, will start from negative infinity and behave as such. So the behavior reaches infinity, positive or negative, around the vertical asymptote, around x equals negative 5 over 2. So therefore, since the y value has no limit, it reaches an undefined value, we say that the limit does not exist. The third limit we'll do is the limit on the function as x approaches plus or minus infinity. Plus or minus infinity represent the end behavior. So when x approaches plus or minus infinity, that means you're looking for end behavior. And an end behavior for different functions would look different. But for a rational function like the one we have right now, this function's end behavior is a horizontal asymptote. So when we're trying to find that limit, we say that the limit for this function altogether is identical to the limit of the highest degree term, which is in this case x in the numerator, over the highest degree term in the denominator, which is the 2x. So the limit of the function as x goes to plus or minus infinity is identical to the limit of x over 2x. And when these x's cancel out, you're left with 1 over 2. So that would be the final answer. That will be the limit of the function as x goes to plus or minus infinity. And therefore, if f of x is approaching half when x approaches plus or minus infinity, therefore y equals half is a horizontal asymptote. That would be the basic limits exercises that you would get. From here on, we will do a bit more advanced limit solutions and solving limits by factoring. In this function, I'm given the limit as x approaches 3 for x squared minus x minus 6 over x squared plus x minus 12. The first step you should take is substituting the value 3 in the x values. But that will yield 0 over 0. I encourage you to try that, please, and check for yourself. Now, in that case, we will know that since the answer is 0 over 0, which makes the whole ratio an indeterminate ratio, therefore, there exists a hole. That backwards E symbol means there exists. There is a hole in that rational expression at x equals 3. A hole simply is a point where the x value gives no y value. Now, the limit for this function could be found by factoring the numerator and the denominator, as you can see here. The x minus 3 into x plus 2, if you expand it, you'll get x squared minus x minus 6. The x minus 3 into x plus 4, if you expand it, you'll get x squared plus x minus 12. We can quickly notice here that the x minus 3 factor is common to the numerator and to the denominator. So we're going to cancel that common factor out. What you're left with is the limit of x plus 2 over x plus 4 when x is approaching 3. Now, x equals 3 does not render the denominator 0, neither the numerator. And in this case, we can substitute now x equals 3 into the function, and we come up with a limit equal to 5 over 7. In other words, when you have a hole, there'll always be a limit from the left side of the hole and the right side of the hole. So as the function approaches the hole from the left, in this way, we're moving in that direction, the y value is going to get as close to 5 over 7 as possible. Same thing if the function approaches the hole from the right, the y value is going to approach 5 over 7 as much as possible, and therefore the limit is 5 over 7. Here we speak about left side limit and right side limit. So the limit of the function when x approaches 3 minus, so if x equals 3 in this case, at this value, when the limit as x approaches 3 minus, which is 3 from the left, that limit is equal to 5 over 7, and as well when x approaches 3 from the right, so we're talking 3 plus in this case, 3 from the right, the limit is also 5 over 7, and there exists a limit at the hole, which is always true. At a hole you'll always have a limit, since the limit of the function as x approaches 3 minus, or 3 from the left, is equal to the limit of f of x when x approaches 3 plus. That will be the end of the first lesson about limits. I encourage you to find exercises in your textbook and do practices to improve your abilities. The second lesson about limits will be related to some review to factoring limits, one more example about factoring limits, and extra material we'll see in a minute. So the limit we're looking into right now is x squared minus 4x over x. I'm going to find the limit to x squared minus 4x over x when x approaches 0. Again, if we substitute x equals 0 into that function, we will get 0 over 0, which is indeterminate, and there exists a hole at x equals 0. So we're going to try factoring. That's our strategy. We substitute first the value, x, whatever x is approaching. If that didn't work, we try the factoring. Upon factoring, we realize that we can factor x from the numerator, and that will help us see that we can cancel out the x values from the numerator and the denominator. And as a result, you'll end up with the limit of x minus 4 as x approaches 0. Now it's the time to sub in x equals 0 in here, and you get the limit to be negative 4. Now graphically, let's see what that looks like. That x squared minus 4x over x function we have in the top of this page, this function is nothing but the line x minus 4, but there exists a hole at x equals 0. So if you draw the line where the x-intercept is 4 and the y-intercept is negative 4, and you have at x equals 0 a hole which is at negative 4, you'll see as well that as the function approaches x equals 0 from the left, the y value is approaching negative 4. And if x approaches the 0 from the right, you'll see the y approaching negative 4 as well. Therefore, the left side limit, again, this is the left side limit when x approaches 0 minus, will be equal to the right side limit when x approaches 0 plus, which is both equal to negative 4. And that will be, again, a review or another additional practice on factoring to find the limit. The third topic is about rationalizing to solve a limit. Now, rationalizing to solve a limit is a bit tricky if you don't know some rules, some very important rules. Let's begin with this example. Limit as x approaches 0 for the function square root x plus 4 minus 2 all over x. Again, if you substitute x equals 0 in both x values, you will get a 0 over 0, which is indeterminate, and therefore we have a hole at x equals 0. In order to solve this limit, we're going to try to get rid of that radical sign. In order to remove a radical sign, you have to apply its inverse function. So technically, I need to square that. By squaring the radical, the square root, I can remove the square root. But in the same time, if I just square everything, I will apply the FOIL method, or I'll simply expand, and I will end up again with another root function. So I might square this and square that, but the exponent 2 times the first expression times the second expression will still yield a radical sign. So this is where we depend on knowledge we obtained in grade 10 when we tried to factor expressions like a squared minus b squared. The answer to that is a minus b into a plus b. So we look here, we see that's my a, the root x plus 4 is my a, minus b, that's the 2. So if I multiply it by a plus b, both the numerator and the denominator, because all that had to be equal to 1, so I don't change any of my function. And therefore, in this case, you just square, you localize raising it to power 2. Therefore, you square root of x plus 4, and that will yield x plus 4, minus, so we're following a squared, minus, then b squared, 2 squared becomes 4. And if you simplify the numerator, you'll end up with just x over x into root x plus 4 plus 2. Now we can cancel the x values, and you're left with 1 over the square root x plus 4 plus 2, and the limit as x goes to 0. I would like to insist on something that I didn't do before, which is always writing the limit expression. You always keep the limit expression with your work until you're ready to give your final answer. Once you're ready to give your final answer, when you substitute the x here equal to 0 in that x value, this is where you don't write the limit anymore. So this graph we've seen above, even though it does look a bit weird, looks scary, but yet it has a limit as x approaches 0. There is a hole at x equals 0, but the limit exists and its y value is 1 over 4. Another expression for rationalizing to solve limits is limit as for a cubic root of x minus 2 over x minus 8 when x approaches 8. You'll begin by subbing in the 8, and you realize you end up with a 0 over 0. You have an indeterminate expression, and there exists a hole at x equals 8. And here we'll try to rationalize again. So how do I get rid of that cubic root expression? I need to cube. So you need to apply the cube. But to apply the cube, that's going to be, if I say cube the whole numerator, that's going to yield 4 terms in that polynomial upon expansion. And as a result, you'll still keep that root sign. So we're looking for a conjugate. I'm starting to talk about a conjugate here. In this exercise, in the previous exercise, this expression represents the conjugate to that expression. In other words, here, what would I multiply? I'll use this formula, a minus b with, to get a cubed minus b cubed, since I want to cube only this and that. So the conjugate to that would be a squared plus ab plus b squared. And that's another equation that you should probably have seen in grade 11. You also see this in MHF4U course when you learn factoring polynomials. You can do factor theorem, and you can factor the following cubic expression, difference of two cubes, and you end up with that as a quotient. Now applying it here, the a cubed is the x, the b cubed is the 8. The a is the cube root of x, and that should be obvious. If you cube root a cubed, you get a. If you cube root x, you get cube root x. So minus 2, so that's the b. Now to follow that formula, if that's a, cube root x, and that's b, that's the 2, you square the first one, so cube root x squared, plus you multiply the a by the b, so 2 cubic root of x, plus b squared, which is plus 2 squared, which is 4. So now I'm going to multiply the numerator and the denominator by the conjugate of cubic root x minus 2. Again, this one here is the conjugate of that expression. We don't even need to worry about expanding, doing the FOIL approach. We don't need to worry about that, because since these two are the conjugates, therefore the product is going to yield that a cubed minus b cubed. So we end up with x, so cubic root of x cubed becomes x, minus 2 cubed is 8, over x minus 8, what we have in the denominator here, times that expression. Cubic root of x squared plus 2 cubic root of x plus 4. Now we can cancel the x minus 8, and you're left with substituting 8 into the x value, and you end up with 1 over 12. That will be the end of this lesson. Next lesson, we'll work on substitution method. Solving by substitution, you get the same expression I've given you before, the lesson before. So we go with rationalizing. That's the same expression. I've done it with rationalizing. I'm going to do it by substitution. In this case, instead of trying to find a conjugate, you're going to try to replace a complex expression, like the cubic root of x here, by the letter u. Once you've done that, you have to replace every single x value in this expression by u. So the cubic root of x is u. If you cube both sides, you'll get x equals u cubed, as we've seen here. Therefore, this expression becomes u minus 2 over u cubed minus 8. But now we still have x approaching 8 we cannot keep. We have to change it to u. So if x approaches 8 and u is cube root of x, substitute 8 in the x, and you'll find that u will approach 2. Now we end up with this expression, which we should easily see as that's the difference of two cubes. U cubed minus 8, we can factor it using the rule we've seen here. U cubed minus 8 will fit into this rule. Take the time to do it slowly, but the final outcome is u minus 2 into u squared, square the first, plus the first times the second, plus square the second. Again, we can cancel u minus 2, and you'll end up with 1 over u squared plus 2u plus 4. This is where we substitute the u value, and you end up with the same answer as we had before, 1 over 12. Again, this was 1 over 12 as well. Whether you go substitution or rationalizing, it is the same. Another example about substitution. The limit of x power 1 over 6 minus 2 over x power 1 over 3 minus 4 as x approaches 64. So here I can quickly realize or notice that if I square x power 1 over 6, it will become x power 1 over 3, because you multiply the exponents. So x power 1 over 6 times 2 is x power, I'll put it here, x power 2 over 6, which is x power 1 over 3. So here I'm noticing that this is a difference of two squares. I'm noticing if I need to square the x power 1 over 6 rather than cube it. So here I'll see a minus b into a plus b equal to a squared minus b squared, the difference of two squares. So again, I'm going to look for the conjugate of this expression. So that would be the conjugate of that expression. And again, I multiply it both to the numerator and the denominator, so we don't change the final outcome of the function, as if we're multiplying by 1. Now, if you're going to expand these, it'll take you some time. We already know that this is the difference of two squares. So you square the first, x power 1 over 3 squared. You get x power 1 over 6, squared. You get x power 1 over 3 minus 2 squared is 4 over this expression times that expression. X power 1 over 3 minus 4 times x power 1 over 6 plus 2. We can easily see that we can cancel out these two expressions, and you're left with 1 over x power 1 over 6 plus 2. Now it's the time to substitute x equals 64, and you end up with 1 over 6th root of 64 plus 2. Another method of doing this is by doing the substitution method. Again, let u equal x power 1 over 6. So you square u and you square x power 1 over 6. U squared equals x power 1 over 6 all squared. And you end up with u squared is equal to x power 1 over 3. Now if x approaches 64, therefore u will approach 6th root of 64, as if I'm substituting in here 64, and that will be u. Again, replace x power 1 over 6 by u, minus 2 over u squared, which is the x power 1 over 3 minus 4, when u approaches the 6th root of 64. Use the difference of two squares. A squared minus b squared is a minus b into a plus b. So we know what's the a, that's the a, the u is the a, the 2 is the b. Now we could cancel out, and you're left with 1 over u plus 2, which when you substitute the u's value, you end up with the same result we had in the previous exercise. I'm going to go back to show you. Again, the same result in here, like the result we've seen in here. The last limit type exercise we'll learn is the absolute value. You're given a limit as x approaches 1 with absolute x minus 1 over x minus 1. And here again, if you substitute x equals 1, you will realize that you get 0 over 0, which means that there is a hole, and there exists a hole at x equals 1. So two cases have to be considered. First, if x minus 1 inside the absolute value is greater than 0, in other words, if x is greater than 1, or since it's greater than 1 means x is approaching 1 from the right, so x approaches 1 plus, then we don't need to keep the absolute value anymore. We just write it as x minus 1. But if x minus 1 is less than 0 and x is less than 1, therefore we're approaching 1 from the left, so x approaches 1 minus. And in this case, the absolute of x minus 1 is the opposite of x minus 1 to make sure that that outcome is always positive. The answer of absolute functions is always positive, or 0. Now, the limit of this expression, as x goes to 1 minus, we realize if x goes to 1 minus, instead of absolute x minus 1, we'll replace it with negative into x minus 1. And here, we can cancel out, and the outcome is negative 1. But as x approaches 1 plus, the absolute value of x minus 1 yields x minus 1. And when you cancel this out, the final outcome is 1. So the limit as x goes to 1 minus, or approaching 1 from the left, is not equal to the limit when x approaches 1 from the right. And as a result, the limit does not exist as x approaches 1. The second type exercise I'm going to produce here is limit of absolute function of x squared minus 5x minus 6 over x plus 1 as x approaches negative 1. So we're looking for where is x squared minus 5x minus 6 is positive. So we look first factor it, find the two roots, they're at negative 1 and 6, and use the number line to determine where is that function positive. This is a quadratic equation, positive leading coefficient, so it's going to be above the axis, above the x-axis, less than negative 1, under the x-axis between negative 1 and 6, above the x-axis after 6. So it's positive in these two locations. So as x approaches negative 1 from the left, this function is positive, because that's what we're interested in, negative 1. And if we want to consider it negative, if x squared minus 5x minus 6 is less than 0, we realize that if x approaches negative 1 from the right, therefore the function is negative. So if x goes to negative 1 plus, that expression is negative. If x approaches negative 1 minus, that expression is positive. Well, that's important because we cannot keep the absolute value, we have to remove it. And if we remove it, we have to know when do we multiply by a negative, when we don't. So here, when x approaches negative 1 minus, we said negative 1 minus is where the function is positive. Therefore, when we remove the absolute value, we can leave it as is, but we just factor, and now I can cancel and substitute negative 1 in there, and I get negative 7. But when I go to limit as x goes to negative 1 plus, negative 1 plus is where the expression is negative. So when I remove the absolute value, I have to multiply by a negative sign to keep everything positive, since all this is negative now. So by doing that, when you simplify, you end up with negative into x minus 6, which when you substitute negative 1, you're going to end up with a 7. Therefore, the limit to the left is not equal to the limit to the right, and therefore the limit does not exist. That's the end of this lesson.